Welcome to week 6. We're over halfway. This is the first lecture of 2. We finished up looking at envelope considerations last week. We're now going to move into mechanical considerations for the next couple of weeks. In this week, at least in this first lecture, we're going to look at the very first or the most common consideration, and that's the concept of setback. Now, quickly, mechanical considerations happen in both general areas that we look at during an energy audit. So, mechanical issues fall both into the consumption issue, in other words, the equipment running that does not need to run, so run hours, that type of thing, and we also get efficiency issues. The equipment could be more efficient. So this happens to be in the realm of the equipment's EER or COP or the SEER, the SEER rating. So these things are efficiency issues. But again, mechanical issues fall in both consumption and efficiency. First thing I want to look at is something called temperature setback. The reason I'm looking at this is this is one of the more common considerations that show up when looking at HVAC equipment, and especially the federal government, if they're paying for an energy audit, they'll usually give you a suggested list of things that they want you to look at. The idea of temperature setback is always at the top of the list. So if you don't know how to do any other thing, having a look at temperature setback and at least when it's applicable and what are the impacts on it are a valuable tool. So the idea of setback is to have an occupied design indoor air temperature and an occupied design indoor temperature. So you're basically going to shift the design temperatures. In theory behind this, you're reducing the delta T in our energy transfer equations. So if you look at all the equations that have a delta T based on indoor and outdoor air temperature, both conduction, in other words, heat transfer across a building envelope, the U times A, and there's that delta T. Now remember, when we looked at envelope, we were concentrating on reducing the U. In this case, we're trying to lower the delta T part. Again, both items, the end result is to try to make the BTUs per hour heat transfer smaller. Now, the delta T, that same delta T, also shows up in anything having to do with convection. So infiltration, ventilation, makeup air, exfiltration, anything having to do with convective heat transfer has that same delta T. So lowering the delta T impacts heat transfer from both conduction, convection from ventilation, convection from infiltration, convection from makeup air, convection from combustion air, you name it, it impacts all those. So setback overview, again, heating setback, the whole idea is to reduce the delta T. In this case, we have an occupied set point. The delta T is the difference between that occupied space temp and whatever the outdoor air temp is. That's our delta T. Setback means I'm going to take this occupied set point and reduce it, make it lower in heating. So if we look at that same outdoor air temperature, I've reduced the delta T. So I've reduced the delta T, at least in the heating mode, by reducing the occupied set point. Cooling works the opposite direction. It still means that I'm reducing the delta T, but I'm actually raising the set point. So I have an occupied set point here against some sort of hot outdoor air temp. So I have this large delta T. When I become unoccupied, I let the occupied set point get higher, which makes the difference between that hot outdoor air temperature and my set point less. Again, the objective here, reduce the delta T. Now, setback considerations. There's some key considerations when contemplating setback. Should I do setback? How much setback? What's good, what's bad? There's three real key areas that impact setback. The first one, the zone that I'm considering setting back, does it have a distinct occupied and unoccupied time? In other words, can I even use setback? Obviously, if a zone doesn't have unoccupied time, in other words, there's people in there all the time, setback doesn't even come into play. How long does the occupied and unoccupied times happen? In other words, am I running 2 shifts and I only have the 3rd shift unoccupied? Or is it the opposite? I'm running 1 shift and I have 2 shifts unoccupied. That'll have more of an impact on how much setback I can use. The next consideration, how much mass is in the interior of the zone? And when I'm talking mass, I'm talking things that are large, heavy. They're made out of large quantities of metal. They're made out of large quantities of masonry product, chimneys, granite countertopping, large industrial machinery, anything that takes a long time to either heat up or cool down. Those are massive items. I'm not talking about small things like chairs or things that easily change temperature or don't take a long time to change temperature. So how much mass is in the space? And then finally, whatever HVAC equipment I have currently covering that zone, is it able to deal with recovery from setback? Certain types of HVAC equipment are not well equipped to handle coming back from setback. So, dealing with the amount of setback, you only want to impact the zone's air. You don't really want setback long enough to affect the mass within the building unless you're truly setting back the temperature for a long period of time, like a school system that's unoccupied during the summer months. Then it doesn't really matter. I know it's going to take a long time to recover when fall comes, but I'm okay with that because I'm going into a prolonged period of unoccupied. But if the unoccupied period is not more than a fair length of time, then I have to be careful that I don't want to impact the mass within the space. And the more mass of the items, the more danger I get in because they don't recover fast. If the mass in the zone changes temperature, it's harder to recover. Now, I can easily recover air temperature, but the mass, I'm sure a lot of you out there have gone into buildings where they've had setback, you've walked in, the air temperature still has sort of a coolish feel, but when you walk over to the thermostat or sensor, it says that it's at set point, but you go near tables, chairs, pieces of equipment, and they're cold. Well, through radiant, they're going to keep sucking energy off your body because it takes a harder time for the mass to change. Occupancy plays a role. Internal mass plays a role, and the type of equipment impacts how much setback will work. So first of all, the amount of occupancy. The shorter the unoccupied period, the greater the amount of setback that I can use. The reason for that is I'm not going to be unoccupied for that long a time. If I'm only unoccupied for a single shift, I can let the air temperature float farther. In other words, I can set the air temperature back farther and still not risk losing a ton of heat off my mass. Again, the shorter the unoccupied time means there's less time for the mass in the zone to lose temperature. Easier to recover air temperature than mass. And again, speaking of mass, the greater the amount of mass items in a zone, the smaller the setback that I can use. Massive items, again, include a lot of stone or masonry items or large metal objects. Production equipment comes to mind. Chimneys, countertops, whatever. The theory, you don't want a large mass of items to lose temperature. It's harder to get back. So if I have areas with really large, massive pieces of equipment, I want to be careful on the setback, because if those large masses start losing temperature, really difficult to return. And when people work in front of those masses, it pulls their energy off their body through radiant. HVAC equipment. Certain HVAC equipment is not capable of rapid temperature recovery. So temperature recovery is similar to from setback. Heat pumps, for example, only have a discharge air temperature in the mid-90s. This is a lot lower discharge temperature than a fossil fuel piece of equipment. So heat pumps in particular have a terrible time recovering from setback just because of their low temperature discharge. So setback, the amount of setback will ultimately be decided on the occupants and the productivity of the zone. When you start implementing setback, you want to watch productivity. If it's adversely impacted by the setback, you're not saving anything, so you have to adjust accordingly. So ultimately, this particular recommendation will be very dependent on how much you're impacting the productivity of the customer's building. The setback calculation, when you first look at it, it looks fairly complicated. Some of these hand calculations get a little cumbersome. If you look at it closely, it still resembles a lot of the previous hand calculations. In this case, we have both a heating calculation and a cooling calculation. And what I want to do is concentrate on the front end of this formula. So if we look at the equation breakdown, the very first thing that happens is we calculate the U times A for all zones in the envelope that are going to be impacted by the setback. So if a zone includes part of the roof, some walls, some windows, some doors, I need to calculate the U value for all those components, multiply by the area. Now, the units that we're left with, when I multiply all these U times A's, in other words, U value times area, when I cancel the units out, I get BTUs per hour per degree Fahrenheit. You need to remember that, BTUs per hour per degree Fahrenheit. The next part of the equation has 1.08, this happens to be the convective portion, times both infiltration and ventilation. In other words, two of our key sources of convective heat transfer. Both infiltration and ventilation need to be in CFM. Now, once they're in CFM, I can add the two together, and then when I multiply CFM times the 1.08, look at what units I get. So the units of 1.08 are BTU minutes divided by hour degree Fahrenheit cubic foot times CFM, which is cubic feet per minute. I'm left with BTUs per hour per degree Fahrenheit. Does that look familiar? When I did the conductive portion at the first part of the formula, I ended up with BTUs per hour per degree Fahrenheit. Because they're the same unit, I can add them together now. So now I've combined all the heat transfer between conductive and convective, and I now have them in a form of BTUs per hour per degree Fahrenheit. The rest of the equation, if you go back and look, are similar to what you did before. I can either use a correlation, weather data, I can use heating degree day. There's a lot of different things that I can use. Most often they use correlation data because I need the weeks of a season. Anyway, the equation breakdown, the heating saving setback, this is the number of degrees difference between occupied heating set point and unoccupied heating set point. Same thing with cooling. The rest of the equation is similar to the envelope equations. Now, if we look at an example, and hopefully you'll get used to this, a lot of these problems are lengthy story problems. Now in this particular case, we have a building located in Fort Wayne, Indiana. The particular zone that I'm contemplating setback is described as follows. It's a top floor of a 4-story building. The area is 100 feet by 75 feet with a ceiling height of 10 feet. The U value of the roof is as follows, and I'm not going to read the whole rest of it. But trust me, there's enough information in here to actually do that hand formula for setback. There's a very regimented set of steps to go through to calculate this. First of all, calculate all your areas. What are the areas of my window? Then you calculate walls. Now be careful in this step. Once you calculate the walls, you have to subtract out the area of the windows. Common mistake people do. When they get to the walls, they leave the walls in the gross and not the net. In other words, subtract the windows out. And then finally, the roof. Calculate the U values for the 3 components. Then finally, multiply the area times the U value. It'll give you a BTUs per hour per degree Fahrenheit. These can be added together because they have the same units. Step 2, calculate infiltration. In this case, we're doing a CFM per foot of crack. We're going to determine the length of crack needed to be looked at. The foot of crack per window times how many windows will be considered. So now we have total linear foot of crack being considered times the CFM per foot of crack gives us CFM. I now have the CFM of infiltration. I do the same thing with ventilation. I need so many air changes per hour times the zone volume divided by 60. It could be CFM per person, depending on ASHRAE standard 62, whatever. I need total CFM of ventilation. In this case, for this building, I need a total quantity of 1,250 CFM. I can add those two together, the 1250 plus the 187.5 times the 1.08 gives me BTUs per hour per degree Fahrenheit, which means I can add it to this other value. On the winter side, I know how much setback I'm doing. The average length of the winter season for that area, Fort Wayne, I got that from my correlation weather data. The hours per week setback that I'm going to be able to do times the cost for my fuel divided by the fuel efficiency and divided by the BTUs per CCF gives me a cost savings. I work the same thing on my cooling side. Down here happens to be the Fort Wayne, Indiana correlation weather data. You'll notice this 28.5 week length of the winter season under heating. That's where this came from. Also, the 22.5 weeks for the summer season came from here. What this does is this ends Lecture 6A. When you're ready, you can proceed to Lecture 6B.